Hello, Dr. Ko. My name is Shazeb Ahmed, and this is homework 5, which is also the second part of exam 2. So in this video, I'm going to be writing a Python code uh, to solve for a problem. So the problem is that there's going to be a network, and we're supposed to calculate the water flows through each pipe segment and also the net flow in and out of the source and the sink nodes. So all the elevations are 0 meters except for node 0, which is at 30 meters. And node 4 is fixed at 0 pascals, while node 0 is set to 200,000 pascals. And the diameters of all pipes are 0.1, and they all have a relative roughness of 0.001. So without further ado, let's get started. So the first thing that we are going to do is import numpy as np, and we're also going to do from scipy.optimize import Newton, root. So top line basically imports numpy, and the bottom line is a pre-coded library that imports the Newton solver. So that's that. So I'm going to do Shift Enter. So now we're going to define some global variables. So the first one that's going to be is force due to gravity, which is 9.81. And we're also going to define RHO, which we're going to say is 1 e to the third, which is the density of the fluid. And we're also going to define the viscosity of the fluid. And we're just going to do mu is equal to 1 e to the negative third. Also going to define the diameter, which is 0.1, and also the ED, which is 1 e to the negative third. All right, so now we're going to calculate the friction factor using the Churchill correlation. So I'm going to write this out first, and then I'll let you know what I wrote out. So we're going to define F as equal RE and ED colon. So we want something to calculate the friction factor, provided the Reynolds number and also the roughness of the pipes. That's what RE is, and that's what ED is, the roughness of the pipes. So now we're going to calculate A in the Churchill correlation, and that equals to 2.457 times NP dot log parentheses 1 over we're going to do another parentheses 7 dot divided by RE raised to the 0.9 plus 0.27 ED, and we're going to put a parenthesis out there. I almost forgot to put a parenthesis in the beginning, and we're going to raise all of that to the 16th. Next, we're going to calculate B. So B is equal to B in the Churchill equation. B is equal to 37530 divided by RE. There we have B. And next, we want to return the friction factor, and it's going to be 2 times 8 over RE raised to the 12th plus 1 divided by A plus B. I'm going to raise that to the 1.5, and we're going to raise that to the 1/12. Alright, invalid syntax. Let's see where I messed up here. So A is equal to 2.457 times np.log. Then we have 1 divided by 7 dot divided by RE raised to the 0.9 plus 0.27 ED, and that's all multiplied by 16. So don't see invalid syntax line 2. So we have 2.457 times np.log parenthesis 1 divided by 7, or don't know what the situation is there. (2.457) times np.log . Okay, I'm gonna try and retype this out because I can't find my mistake. So we have 2.457 times np.log. I'm gonna do 1 divided by 7 divided by RE, all raised to the 0.9 plus 0.27 times ED. I'm going to raise all of that to the 16. Okay, there we go. Okay, so the next thing that we're going to do is, since we're going to calculate the delta head of the nodes given a flow of Q, so which is head at the two nodes and minus the head at the from nodes of where they're coming from and where they're going. So we're going to do define for delta head. We're going to use d head, and we're going to do Q comma L comma K and comma D and comma ED. So we're going to define the delta head given the length, the fitting of the pipes, the diameter of the pipes, the roughness of the pipes, and of course Q, which is the flow rate of the pipes. So now we're going to calculate the velocity. So we have V equals NP dot absolute value, and this ensures that we don't end up with a negative Reynolds number. So we're going to do Q divided by NP dot pi multiplied by the diameter raised to the 2 over raised to the second raised to the 2 over 4. And then we're also going to calculate the Reynolds number given the density and the viscosity. So we have RE is equal to RHO multiplied by V multiplied by D divided by MU. and that calculates the Reynolds number given density and viscosity. And now we're going to return the delta head. So that's going to be negative NP dot sine Q multiplied by K plus 4 times F parentheses Reynolds number and the roughness times L over length over diameter. I'm going to multiply that by V, which is the velocity, raise that to the 2 over 2. We're going to divide that by G. And this should return the delta head. Okay, great. So now that we have the delta head, now we're going to calculate the flow of the pipes. So we're going to define flow as delta head and given the length of the pipes, given the K values, given the diameter, and also the roughness of the pipes. Alright, great. So we're also going to do the same thing that we did in the last step. We're going to ensure that there's no negative Reynolds number. So we're going to do DH underscore ABS is equal to NP dot ABS, stands for absolute value, and in parentheses delta head. Don't know why that is popping up. So we have value. So now we're gonna take care of the situation where the delta head is extremely small, for which the Newton solver has difficulty converging. So we're gonna do an if statement. So if the absolute value of the delta head is less than, we'll do 1 times 10 to the negative 10th. And we're going to return 0.0. So it'll always return delta head as 0.0 if the absolute value is less than 1 times 10 to the negative 10th. So now we're gonna solve for the initial guess for the flow rate, and we're gonna assume a reasonable guess of 0.1 for the fanning friction factor. So we're gonna label this Q guess equals NP.pi multiplied by diameter raised to the 2 over 4 multiplied by NP dot square root, and multiply that by absolute value of the delta head and divide it by the K value plus 4 times 0.1 times L over D, and we're going to do that multiplied by 2 and multiply it by the force of gravity. So now we're going to define the function to 0. We calculated the delta head based on the iterated flow rate Q, and the flow rate Q must be equal to the delta head. given that given the function is to 0. So for this next step, we're going to define f underscore 0 for q, and we're going to return d head, flow rate using L length, K value, diameter, and the roughness, minus the delta head absolute value. So the resulting flow rate is equal to the Newton of F to 0 and the Q guess. And we're going to return the delta head for the correct directionality. And to do this, we're going to do return np.sine delta head multiplied by resulting flow rate. And yeah, I think that should be it. Hopefully this runs. Alright, cool. So our next step is, how do we put in the values for the pipes, like the lengths and the K values and the to nodes and the from nodes, like which way is the flow. So in order to do that, we're going to create a two-dimensional array for all of the pipes. So it'll be something like pipes is equal to np.array, and here we're going to do our first node, and we have parentheses, so now we're going to place brackets. So for the first one, it's from node 0, it's to node 1, and the length is 1.5, and the K value is also 1.5. And for the second one, it'll be 0, 2, 2 dot, and 2 dot. And for the third one, it'll be 1, 2, 1.5, and 0. And for the fourth one, it'll be 1, 3, 1.5, and 0. And then for the next one, it'll be 2, 4, 0.5, and 0. And for the last one, it'll be 3. That's not what I want to do. it'll be 3, 4, 3 dot, and 2. Okay. Okay, I forgot to place a comma after all of these. Comma. 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 And comma. Alright, so that should do it for the arrays. I'm going to make sure these values are correct before I move on to the next step. 0, 0, 1, 1, 2, 3, 2, 2, 3, 4, 4, 1.5, 2. Alright, look at. Okay, so now I'm gonna input the elevations of the nodes, which is in meters. So we're gonna call that variable z. So it'll be z np.array parenthesis brackets. So we said node 0 is the only one that's 30 meters, and the rest of them are 0. So 0. So now we're gonna input the pressure of node 0, which we said was 200,000 pascals. So it'll be the external pressure is equal to np.array in parentheses brackets 2e to the 5th, same thing as 200,000 of node 0, and external node is equal to 0.4, which is the node 4 pressure, which is 0. Now we're gonna define for the nodes from which the flow is coming from. So that'll be the first column of arrays, these numbers right here. And in order to do that, we're gonna do from nodes is equal to pipes, and we want the column, and since they go from like column 0, 1, 2 instead of 1, 2, 3, we want the first column, so it'll be 0 column. So that's going to be as type np int 32. Now we're going to do the same thing for the 2 nodes, and that's going to equal to it's going to equal to pipes. We want the second column this time. We don't want anything to do with rows, so we're just going to put a colon for that, and 2, 1, sorry, gives us the second column. And we're going to do it dot as type np integer 32. Alright, great. So that gets us the numbers for the nodes from which the flow is going into. And next we're going to be doing the lengths of the pipes, which is the third column. So we're going to do lengths equals pipes from this array. That's why I keep typing pipes. and disregard rows, and it'll be the third column, so it'll be 0, 1, and 2. And that gives us the lengths of the pipes. And next we're going to get the K values, which is the final and fourth column, and that'll be K is equal to pipes, and we want colon, comma, 4. Sorry, 3. Alright, great. So we want to define the number of pipes, which is essentially the same number of rows for this pipes array. And we're just going to do n pipes is equal to pipes dot shape 0, which gives us the number of pipes, which is also the number of rows. And next we're gonna want to get the diameters. So pipe diameter is equal to np dot full n pipes describe the diameters of the pipes, and then we're going to do the pipes and their relative roughness. So we'll do pipe underscore ed is equal to np dot full parentheses n pipes comma ed. So next we're going to calculate the indices of the internal nodes. So we're going to do something like n nodes is equal to parentheses np dot max, and I'm going to type this out first and then I'll explain what I did. Pipes, no idea why that keeps popping up. So np dot max pipes, and then we're going to do brackets. So we're going to want the second column, and it'll be as type np dot int 32 plus 1. So the heads is equal to np dot zeros for the number of nodes, and the heads we're going to do external nodes equal to external p divided by rho divided by g, and add the elevations of the external nodes. So the reason I just did this is that the number of nodes will be the maximum in the column for 2 nodes, because the numbering of the pipes is always from lower index to a higher index. So we add 1 because the index is starting at 0 and we want it to start it as 1. Alright, let's see if this runs. Fingers crossed. Alright, so I have an error in that line. So pipe, this was supposed to be full. Pipe D, end pipes is not defined. Huh. They're right. It is not defined. I'm making all sorts of typos right now. All right, great. So now that we have that done, we're gonna calculate the flows in each pipe. But first, we're gonna create a list of the internal nodes. So internal nodes is equal to list, and we're gonna set the range for the number of nodes minus the set of external nodes. All right, great. So from the iterated values of the heads, we're gonna calculate the flows through each pipe. So we're gonna do define calc underscore flows of the heads. So the flows are equal to np.zeros of n pipes, and for I in range of the n pipes. Colon there, and delta head is equal to heads brackets 2 nodes brackets I minus the heads of the from nodes. So that'll be from nodes brackets I, and the flows FLWS, flows I is equal to flow parentheses delta head lengths of I k values pipe diameter and the pipe ED roughness. And then we're going to return the flows. So now from the flows through each type, we're going to calculate the net flow for all of the nodes, internal and external. So for that, I'm going to move down a little bit. So I'm going to do define calc net flow rates. I'll do that, and the net flow rates for all the nodes is equal to np.zeros and nodes and then we're going to do np.add at the net queue for the 2 nodes and the flows. Excuse me. And we're also going to do np.add at net queue from nodes, and this is going to be negative flows because from nodes is the flow leaving the node, which is negative. And we're going to return the net Q. Alright, great. So now we're gonna find the roots, the zeros. So the net flow for all internal nodes has to be 0, which is achieved by iterating through the unknown internal node pressures. So the net flow for all internal nodes must be 0. And we're gonna now write a function to find the roots, which are zeros. Yes. So we're gonna define net Q internal, and we'll do internal pressure, and it'll be heads brackets internal nodes is equal to internal pressure divided by rho divided by G plus Z internal nodes. And we're going to return the calc underscore net Q, calc underscore flows, heads, in brackets, internal nodes. Alright, let's see if this works. Alright, great. So now we're gonna find the initial guess for the internal pressures, and it's reasonable for us to say that the internal heads are the average of the known external heads. So we're going to write the code now to obtain the initial guess for the pressures, for the internal pressures. So we're going to do internal head guess is equal to np.mean, which is the average of the heads of the external nodes, right? Now we're gonna calculate internal pressure guess from internal H guesses. So we have internal P guess, so we have H is equal to P divided by rho times G add Z. So internal pressure guess is equal to internal head guess minus Z. I'm going to do brackets of the internal nodes times rho times G. Alright. Let's see, what did I mess up here? Don't think I'm supposed to have that. H is equal to P divided by rho times G plus Z. forget to define P somewhere up here. Hold up. All right, there we go. I wasn't supposed to include that. So now we're going to solve for the unknown internal node pressures. Result, which is equal to root, parentheses, net Q, internal, comma, internal, P, guess. And the result dot X. All right, great. So these are the internal node pressures, and don't think we have too much now. So now we're going to calculate the flows through each pipe. So we're going to do calculated underscore flows is equal to calc underscore flows heads. I'm going to do for I in range of n pipes. And we're going to do print f comma from, let's do internal parentheses pipes brackets I comma 0 brackets, I'm going to do parentheses, then I'm going to do this. So we're going to do print f from to int parenthesis pipes. We're going to do I1, I comma 1. Flow is going to be the calculated underscore flows, just I. All right, cool. Let's see if this runs. Okay, that does not look right. So calculated flows heads for I in range n pipes. So we're going to do print f from calculated flows I, internal pipes I1 to did I mess up on? It's a little spaced out. I don't know why it isn't working right now, because this above line of code definitely had the correct values for the results. So calculated flows, heads for I in range, and pipes print F from and pipes I1 calculated flow. Okay, I'm going to. Alright, cool. I will be right back. Okay, so it was just a simple mistake. I just had to run all in order to get the values. So this next part is we're going to find the net flow of the pipes, the pressure, and the elevation for each of the node, and that should bring us to the end. So know that the calculated net flow is equal to the calculated net calculated net Q of the calculated flows of the heads. So we know that the pressure is equal to NP dot zeros of the nodes, and the pressure of the external nodes is equal to the external pressure, and that the pressure of the internal nodes is equal to the result X that we solved for up here. X. Right. And we're going to do for I in range of n nodes. We're going to print F nodes I pressure, comma, pressure, brackets I, and do Z, comma, Z I and the net flow rate as net Q colon calculated net Q. Also going to do I. And all right. This is pressure. I just only added an extra S. All right, great. So there we have all the pressures, the Z values, and the net flow rates. Thank you for watching, and I will see you in the next one.